On December 1st, 1984, a remote-controlled four-engine transport jet took off from Edwards Air Force Base, California, and crashed into a barren patch of nearby desert. This controlled impact demonstration was a joint research and development program by the Federal Aviation Administration and the National Aeronautics and Space Administration. The analysis of CID data continues and will for some time. But the learning process has already begun. The FAA designed the controlled impact demonstration to underscore results of exhaustive research in two areas of aircraft safety: improved crash protection and reduced post-crash fire hazards. Despite the fact that the crash did not go exactly as designed, CID did achieve its primary objectives. The tests did generate a great amount of impact data, including electronic data and over 28,000 feet of film, information that will validate tests used to predict structural damage. New transport seats and restraint systems remained in place and restrained the occupants. New flight data and cockpit voice recorders, including the Navy's Flight Incidents Recorder Emergency Locator Transmitter Unit, survived and worked successfully. Hazardous material containers remained intact through the impact. There is evidence that fire-blocking seat layers protected the seats and delayed the spread of internal flames. Aircraft propulsion and fuel systems operated normally on AMK, anti-misting kerosene fuel. The prototype engine fuel degraders did break down AMK's anti-misting characteristic prior to combustion. Although there was considerable fire and smoke, the AMK fuel did reduce heat transmitted to the fuselage, preventing a burn-through. And the remote piloting system did guide the aircraft down close to the projected impact target area. Finally, the fact that the left wing struck the ground first and neither ruptured nor spilled fuel underscores the validity of the current FAA fuel containment requirements. Though fuel containment testing was not a primary objective of CID, this information has proved useful. The CID's crashworthiness tests were as important to the FAA as the fire safety tests. The crash protection objectives were first, to obtain data on impact forces and their transmission through the structure to the seats and occupants. Second, to evaluate the performance of existing and advanced energy-absorbing seats. And third, to compare tests used to predict structural behavior with an actual crash. But before any of this could be done, the FAA needed a scientifically controlled impact. At the heart of the experiment was the need to find and simulate a common, survivable aircraft accident. To do this, the FAA first had to identify the problems that might cause injuries or fatalities even in a survivable crash. A thorough examination of past accident investigations determined some specific failures: seat mechanisms, restraint systems, seat-to-floor attachments, fuselage and cabin floor structures, overhead racks, galleys, and other components which could cause injuries and fatalities. This work led to the Model Controlled Impact Demonstration. The test called for the CID aircraft to descend at a rate of 17 feet per second, to have a longitudinal speed of 150 knots, and to have a pitch angle of 1 degree nose up with minimum roll and yaw. But it wasn't enough to simply base predictions from this scenario on paper. Prior to the actual CID experiment, there had to be tests. At its technical center near Atlantic City, the FAA evaluated its model accident, first with a series of fuselage section drop tests. Instrumented dummies provided data on transmission of impact forces to seat occupants. A similar test, adding luggage to the cargo hold, measured the cushion this buffer gives upon impact. Sled tests verified longitudinal impact forces. Certainly the largest and perhaps most telling test was the dropping of a scrapped Boeing 707 under the planned impact conditions. Its fuselage survived the shock and remained intact, although the lower fuselage was crushed somewhat and the cabin floor was deformed. The stage was then set for the CID crashworthiness tests. The fire resistance tests were another story. Over the last 6 years, the FAA has examined AMK's potential for protecting commercial transports from ignition of misted fuels. Progressing from laboratory and small-scale tests to full-scale crash tests, all research indicated that AMK would be effective in preventing this problem. The controlled impact demonstration was an opportunity to use AMK in a realistic, impact-survivable crash. To make absolutely sure AMK would be released, 8 wing opening devices were placed in the impact zone. To ignite the fuel, a prime test requirement, the aircraft tail cone was equipped with 2 kerosene burners designed to fire when impact forces reached 1.5 Gs. They would continue firing approximately 9 seconds, the expected slide-out time of the aircraft. In addition, 12 high-intensity approach light towers were installed in the impact zone and the slide-out region, and the ground was covered with railroad trap rock to add extra ignition potential. The CID aircraft's 4 engines were not considered likely AMK ignition sources. Their positions, suspended well forward on the wings, made the chance of ejected fuel reaching them and then actually entering the inlets quite remote. This probability occurs only in the rarest of accidents. From the moment the CID aircraft smashed down onto the desert floor, the model accident was gone. The plane struck the ground somewhat short of the target, with the left outboard engine low and yawed to the left. It remained yawed to the left as it slid into the wing opening cutters. The first cutter entered the right inboard engine at about the 7th stage of the compressor. It slashed through the engine, broke free, then tore through the underside of the wing, inboard of the engine, releasing a massive volume of fuel. At approximately 1/10 of a second after impact, the first ignition occurred on the inboard side of this engine. The highly unlikely had happened. Post-crash examination of this engine showed compressor rotation stopped instantaneously. Why ignition occurred requires a description of the damage caused by this impact. This is an engine identical to the one that ignited, with the cowling removed. Entering fuel is routed to the degrader, where the AMK fuel's anti-misting characteristic is removed, restoring all its normal kerosene properties. It then passes down the right side of the engine to the main fuel pump. When the cutter struck, it destroyed the degrader inlet and outlet lines, and cut through the lines carrying the degraded fuel to the engine fuel pump. It also destroyed the engine gear case, releasing its contents in a misted form. In addition, the hydraulic pump, which is also mounted in this gear case, was struck and released a misted high-pressure hydraulic fluid. The spark that set all this off most likely came from the cutter tearing through the engine. The burning fluids heated the metal case of the engine, which created an extremely hot and continuous ignition source. Meanwhile, other cutters entered the wing and fuselage. Post-crash examination revealed severe damage to the keel beam in the wing box area, massive holes in the lower fuselage through which burning fuel could enter. This rip in the underside of the aft fuselage is an example of the effectiveness of the cutter's work. Similar and even larger openings were made under the wing in several places. Anyone who witnessed the CID test or saw the televised shots of it will probably have the same question. Why did the AMK-fueled plane have such a large fire? AMK is designed to resist burning under crash conditions. It turns to a coarse, nearly incombustible spray. But AMK can be made to fail and to burn violently. It can be sheared too hard, as was done in this sequence by increasing the impact velocity above the protection velocity, which is determined by the amount of additive in the fuel. The only other way for AMK to fail and then burn is to give it an intense, continuous ignition source. In the CID test, the destroyed engine provided just such a source. It stayed with the fuselage throughout most of the slide and was located right at the fuel release point. So, how bad was the fire? Viewing the CID from impact to final rest shows the external fireball about the fuselage lasted roughly 9 seconds. Looking at the fuselage after the initial fireball lifted showed little evidence of heat damage. Paint was intact and only slightly sooted, indicating heat transfer was minimal. Later, the FAA investigated this phenomenon. In these scaled tests, Jet A kerosene released into a 120-knot airstream, allowed to mist, and then ignited, raises the temperature of an aluminum panel 7 feet downstream to 650 degrees Fahrenheit or more. Metal failure occurs above 475 degrees. In the same test using AMK, a noticeable cooling takes place. More of the AMK reaches the metal surface in liquid form, which keeps it cooler. Until all the liquid has evaporated, the temperature of the fluid cannot rise above the boiling point of AMK. In this case, the aluminum panel reached only 200 degrees Fahrenheit. During the controlled impact demonstration, large amounts of liquid AMK evidently flowed over the fuselage, keeping the temperature relatively cool. Because of the lower heat, the AMK fireball did not burn through the fuselage and ignite the interior materials, even though insulation had been removed to install test instrument lines. The fire inside the CID aircraft started with burning fuel that entered the cargo compartments through the holes ripped in the bottom of the fuselage by the wing openers, and possibly through a forward cargo door that opened on impact. This fire caused a quick buildup of smoke in the cabins. The forward cabin visibility was obscured rapidly after the aircraft came to rest. The aft cabin took nearly 20 seconds. Intermittent flames entering the cabin door during the slide appear to be burning fuel vapor, but weren't enough to ignite interior materials. Had there been a sidewall cargo liner in the CID aircraft, as most commercial aircraft carry, there would have been fewer flames and a much longer time for smoke to fill the cabins. These liners were removed to facilitate installation of cables and were not replaced. But could anyone have survived the CID crash? The FAA's answer is, most likely, yes. The fuselage remained essentially intact and was a livable area even though the main structural feature, the keel beam, was severely damaged by one of the wing openers. Nonetheless, all seats remained in place except for one row of triple seats near the floor break in mid-cabin, which was dislodged. Dummies were used to measure impact loads, or forces. Anthropomorphic dummies in white shirts respond like people and were instrumented to record impact forces. The other dummies were medevac types, used to simulate occupant weight only. Impact load pulses recorded throughout the fuselage remained within human tolerance levels. Seat and restraint systems performed as designed. Please note the anthropomorphic dummy in the center seat in this shot, the dummy in the braced position. You will notice that it moves very little during impact and slide out. In this shot, you can tell the pilot experienced severe but survivable impact loads, but was effectively restrained by the shoulder harness. Although we can never be absolutely sure, preliminary findings based on motion picture film indicate some people could have escaped from the aircraft, and existing accident reports indicate passengers in the aft cabin probably could have escaped even after smoke had entirely filled their area. Accident investigators found all 6 exits operable, but not all equally usable. After the 9-second fireball, passengers could have exited through the left forward and right rear doors. The remaining 4 exits were either blocked by fire or of questionable use due to extensive smoke from the external fire. This illustration shows the reconstructed fire and smoke condition for roughly 30 seconds after the aircraft came to rest. For a controlled crash that didn't go exactly as planned, the CID test still accomplished its primary objectives. It yielded extensive impact data and information on the response of an aircraft structure in an actual crash. Since much of the data for rulemaking comes from small-scale and component testing, CID validated the results of previous tests in a full-scale accident environment. And while it confirmed previous research, it also highlighted the fact that accident scenarios are unpredictable. As the analysis continues, the controlled impact demonstration's effect on future aircraft safety will become clearer. Its crashworthiness and its survivability already mark a milestone of aviation safety research.